Okay, so now there's the last section of chapter 6. This is analysis of frames. And they lump together frames and machines. And it's defined as basically structure, right? So we have trusses as a structure, but frames and machines are structures with at least one multi-force member. So a multi-force member has more than two forces. Remember, with trusses, we could break down each of the members into two force members. So that's one of the differences between frames and trusses. And frames typically are designed to support loads. They're usually stationary. And then machines have moving parts, right? Machines transmit these forces. So this diagram here to the left is a frame, right? And if we look at this, let's see, we got the free body of the complete frame, right? So we can do the analysis. We already know how to do the statics analysis, the equilibrium analysis on this frame as a body, right? Free body. We've got the tension of the wire, we've got the weight acting down, and we've got force AX and AY at the bottom. The next step is to determine internal forces of the frame, right? And we could do that by basically taking the frame apart and looking at free body diagrams for each component. Now you'll notice here EB is a two-force member, right? This is like you would find in a truss. So we're already familiar with that analysis. However, this member CEF, right? This is a multi-force member. We've got two forces at C, one force at E, and one force at F. Now notice when you take apart these frames or machines, depending on where you start your analysis, you need to look at the joints here, right? Have equal and opposite forces. So, for example, we do the analysis on this part of the frame, this beam CEF, and if we find this is in tension and oriented that way, and this force acts up, right? Then we can say, okay, well, this force is correct, acting outward, but this force acts down, right? They have to be equal in magnitude and opposite in direction. That's Newton's third law. Let's see, two force members, multi-force members, yes. And we don't necessarily know the line of action for these multi-force members, right? We know for EB, we know the line of action is through the member, right? But we don't know the magnitude. A force like at C, we don't know the direction. And we don't know the magnitude, obviously, either. So we have to represent it as just two generic components. Yeah, and I already mentioned this. Make sure the forces between components are equal and opposite. Typically, you start off with just one of these bodies. You work on it. You figure out the direction of the forces, and then you translate those directions to the opposite or to the attaching body. All right, here's an example of a frame that would collapse without supports, right? If you detached it from A and B, it would just kind of fall apart. You can't really treat this as a rigid body. And notice here, we've got at point A, we would have two reaction forces, and point B, we've got two reaction forces. So let's look at this. If we look at the free body diagram, the free body diagram of the complete frame, right? We've got reaction forces at A, we've got two of those, right? X and Y. And we've got reaction forces at B, two of these. Now, looking at the top here, we've got Cx and minus Cx, right? These forces are equal and opposite. So let's count. We've got 1, 2, 3, 4, 5, 6 forces, right? These four forces are actually two forces, because if we know the magnitude of one, we know the magnitude of the other, right? They're equal in magnitude, opposite in direction. So let's see. If you consider a frame like this, you can actually solve the problem. So yeah, I don't know. This doesn't seem like it's in the right order. If you just took the frame like this, right, you wouldn't be able to solve it. You'd have 1, 2, 3, 4 unknowns. Here you've got 4 plus 2. You've got 6 unknowns. 6 unknowns, and we can write three equations for each of these members, right? We can write some of the forces in X, Y, and some of the moments for this one. And we can write some of the X, some of the Y, and some of the moments for this one. And since we have those equal and opposite reactions, we can solve for these. So basically, the point here is that you're given a problem like this, you look at it, it's like, well, there's 4 unknowns, we really can't solve it. Well, you could if you take it apart, right? Take it apart at this joint, and now you can solve the problem. And before I do an example of frames, I'm just going to throw this one slide in for machines. Machine is basically, you can do the same type of analysis as a frame, except now you're looking at transmission of forces. You have input forces, like for example, this wire cutter, right? You've got input forces on the handle, you've got output forces on the wire. Let's see, given the magnitude of P, determine the magnitude of Q, and you're given some information about this wire cutter's, namely the length, right? Lengths. So we can draw a free body diagram of this thing. And remember, the forces acting on the wire are equal and opposite those acting on the wire cutters at those same locations. So this is what our free body diagram would look like for the machine, which in this case is a simple pair of wire cutters. And now we can take this machine and we can look at each component as a free body, right? Because the overall machine is a non-rigid structure. It's kind of like that last weird looking frame, that two-piece frame we just disassembled. So you can disassemble this, and again you have let's see, 1, 2, 3, 4, 1, 2, 3, 4 forces. Remember, the forces at A, you're supposed to discuss this, but think about why the forces are why the forces at A are such as shown. So pause the video, think about that. All right, so hopefully you're back. And I mean, think about this, right? We've got Q acting downward and P acting downward on this particular section. So AY has to act upward, right? AX we may not know the direction of, but I mean, you can kind of see from this that there's going to be no AX. Same thing here with Q, right? You've got, or sorry, not Q, the bottom half. You've got minus Q, minus P, and minus Y, AY. So these two are pointed up. You need to have something pointed down. So if you do some of the moments about A, you can actually figure out this very simple relationship. This is kind of neat, actually. So some of the moments about A is 0, right? We've got the distance A times the perpendicular times the force P minus, right? This is counterclockwise, so that's counterclockwise positive, and this is clockwise, so it's negative. The distance B times the force Q, right? So you can get a relationship for the force in the jaws of these wire cutters as a function of the force you put in times the ratio of the distance between the handle and this jaw of the plier. So you can see, right, the longer you make the handle A, the larger this force Q is for a given P. And also the shorter these jaws are, right, the shorter the distance to the center of the jaws, again, the larger that force Q is exerted on the wire.